So the definition of electric flux, this is symbol phi E, capital Greek letter phi. E is defined as integral electric field dotted into the cross-sectional surface area. And units of that would be the units of Newton per Coulomb, which is the units of electric field, times meter squared. Or you could say, because the electric field has another alternate unit, volts per meter times meter squared. So that could be volts times meter. So it could have two units, Newton per Coulomb times meter squared, volts times meter. So this is definition of flux. So let's see, what is it measuring? So if the electrical field is going this way, and you happen to have a cross-sectional area like this, you see, so technically speaking, if something is like this, so I'm assuming you've got the electric field like going this way, and then this is my hand, right? And like it's going through it, you see. So then this is kind of a three-dimensional picture. The area vector technically is this way, dA, right? So what you're doing is you're taking little pieces of the area vector like that, dA, then you're taking the electric field and you're taking the dot product of those two vectors. You see, you're taking the dot product. So if they're in the same direction, then the dot product is just going to be EDA. So it's just going to be EDA. In this case, EDA cosine 0, right? Then this is going to be 1. Then you're integrating the electric field along all those areas, right? So if the electric field is uniform across the cross-sectional area of that shape, if the electric field is uniform, then this one reduces to just EA. So that's the simplest version you can just have. A uniform electric field that is in the same direction as the area vector, and then the flux will just be EA. Okay, so now if I bend this way now, so if my hand, I bend it like this, you see, so before I had it like this, so all the electric field is fully going through my hand, you see. So now if I bend it like this, none of the electric field will go through my hand. It will just glide over, you see. So I'm expecting there the flux to be 0. So the electric field goes like this. And let's say the area looks like that, flat. And the dA looks like this. You see? So no matter how strong the electric field there is, it will still produce no flux through that surface, right? So, of course, the angle will be 90 in that case, right? So, EDA, then it's going to be cosine 90. Well, in that case, it doesn't matter if the E is uniform or not, because this is just 0 and the flux is 0. You see? So flux is measuring, therefore, how many lines of electric field penetrate through that surface, and or we can also say cut through that surface, you see. And the measure of that electric field that's actually crossing that surface or cutting through that surface, you see. So now we could also orient the area something like this. Let's say like that, you see. So imagine this was 30 degrees. So imagine now I put my hand on the table and I incline it 30 degrees from the table, you see. So this is from, imagine from here to here's 30. And now the electric field is coming this way, you see. So flat would be like this. This one will be perpendicular to the E field, and then 30 degrees. So then what's going to happen? E dotted into, and then the dA vector comes out of my hand like this. You see? Now, technically, you might say, how do you know the dA vector is going this way or if it's going this way? Can't you say back here, the dA vector is going this way? In that case, what would the answer have been? If you had to define the dA vector this way and the electric field was this way, then the flux would have been negative EA. You see? And then how about here? What if the dA vector you had defined like this? You see what I mean? So if my hand is like this and the flux is coming like that, how do you know the dA is in the direction of the palm or the down this way from the other side? Let's see. For a two-dimensional shape like a hand or some paper, something like that, I don't think there is a formal definition is if the dA is this way or is it this way. I think you could do either one. So if it's a two-dimensional shape, it really, you could say the flux is EA or negative EA. Okay. In this case, it really doesn't matter if you do this way or this way, it's still zero, right? So in this way, you could say the dA is this way or this way. Okay, so then what's going to be the answer? If you define the dA this way, it's going to be let's see, dA, what's going to be this angle? Okay, so let's draw this. Let's be a little careful. If the E is this way, this is your area. This is actually the paper itself, right? And then this is the dA vector. So this is given that it's 30. You see? So when you do the EDA cosine theta, it's this theta that you're doing. It's not the cosine of 30. It's the cosine of 60. You see? So the flux is going to be, let's assume electric field is constant. So it's going to be EA cosine 60, which is going to be what? What's cosine 60? Half, right? EA over 2. You see how it's not cosine 30? So in other words, if my hand was 0 degrees from the table and the electric field was coming this way, what would you do? EA cosine 0, or would you do EA cosine 90? You see, if my hand is 0 degrees from the table, that would be this one, right? You would do EA cosine 90, you see? You see how I didn't use 0 here? So that this is just an application of that to another angle, you see? And then here, my hand was 90 degrees from the table, you see? And then the electric field was coming like this. So I did now, the area is this one. So then I did EA cosine 0. So the fact that I didn't use the angle of the surface from the table, it repeats itself, right? So if you're given this is 30, you got to be careful. Draw a little quick picture. This is the surface. This is the area vector coming out of the surface. And then the electric field makes an angle of 60 with respect to the area vector. So then it's EA cosine 60. Okay. The other reason why it's cosine 60 is it's if you think about it, let's say this is E and this is the surface. It's actually this component of the electrical field that's cutting through that surface, you see. This is, so imagine this is a paper or something. It's this component that's cutting through it. This component of the electrical field, we can call this is the perpendicular component of the electrical field with respect to the surface. You see? And this is the parallel component of the electrical field. It's gliding along the surface, you see? So the flux is a measure of the perpendicular component of the electrical field to the surface, you see? So the area vector happens to be perpendicular to the surface. So we're looking for the perpendicular component of the E to the surface. So therefore, we're looking for the component of E in the same direction as the dA. You see? So it's kind of confusing at first how the angles work. But once you think about it, you see, so okay, so then if this is 30, this is 60, so we want EA cosine 60. Now, if we had defined the dA vector the other way, what would we do? Then it'll be cosine of this angle, right? So the E, what angle the E makes with respect to this dA vector. So it'll be cosine of what? 90 plus 30, which would be 120. So the answer is either EA cosine 60 or EA cosine 120, in which case it's either EA over 2 or EA, negative EA over 2. You see, so the answer doesn't really change much. It's just positive or negative, because a two-dimensional surface doesn't really have a definition for its area. It could be either way. So I'm going to give you another example of this. I was thinking of a comb. You see, so imagine that this is a surface charge, right? And it's creating these electric field lines, and then the quarter is a surface, you see? So now I have maximized the flux through that quarter. The field lines are coming right through that quarter. You see, so when the rest of the world sees a comb, you and I see electric field lines. That's how I want you to think from now on. You see the world differently when you learn physics, right? Every little thing in life has different meaning. You don't just say, oh, wow, what a nice comb from Walgreens or something. You say, what a nice electrical field demonstration. You see, so now what if the surface was like that? What's the flux? What's the flux through that? Right, so what would be that? What's the flux through that if it's like this? No field lines are cutting through that quarter, right? So the flux is 0, right? Cool. And then how about if it's angled? Oops. Kind of like this. Try to view it. Oops. Angle it like that. Ooh, like that. So which view is good here? Maybe, oops, something like this. You kind of can see. You see? So not all the flux lines are cutting through that because it's sitting at an angle, you see? Maybe this view is the best, but it tends to fold. I'm just gonna hold it by hand like this, you see? Like that. You see that? another analogy I'm thinking of flux could almost be the shadow that you cast from the sun's rays. Like if you're here, and if the sun is, so imagine you are, yeah. So imagine the sun is direct. So imagine yourself as like a cylinder like this, you see, and then the sun is like this, and the flux is coming this way. So when the flux lines, when the sun is directly over your head, the full flux lines of the sunbeam go through you. So you basically maximize the flux lines of the sun's rays, you see. Then you cast no shadow, you see. So when the sun is at an angle, you see what's happening. So your area vector is like this. So think of yourself as almost like a piece of paper. Maybe it makes it easier. So when the sun is directly over you, it goes like this. But this is a different way to analyze it. Okay, if you're going to analyze it if you're going to model us as a paper, you say, okay, if the sun is directly over you, and then this is the A, right? Then there's no flux, there's no sunlight going through your body. Okay, I think maybe that's even better. You say, so when there's no flux lines of sunlight going through you, then you cast no shadow. No shadow. But in LA, this could never happen. So you should take my astronomy class to learn why. In LA, the sun is never directly over us. So there's never a point during the year when we will cast no shadow. So the sun will never directly be over us. So we can say when the flux of the sunlight is 0, then there's no shadow. So then the smallest shadow that we get is on June 21. It's the beginning of summer. The sun is the highest in the sky. So the flux coming down like that. So let's say this is this, let's just call it E, but it's not, well, it's actually electric field too. All the electromagnetic waves that the sun is sending, and light just happens to be a portion of that electromagnetic spectrum, right? So in June 21, that's when the maximum flux, you see, a portion of the sunlight goes through you, or actually, I should say it this way, a portion of the sunlight can't go through you because you're an opaque object, right? The other portion of the sunlight just beams down on you, you see. So on June 21, the portion of the sunlight that can't go through you is the minimal. So what's happening? The flux is, so for us, in other words, from LA, you will never have the flux is 0. The minimum for us is on June 21. And you will cast the least shadow. So causes least shadow. Okay, as the months go by, now we're getting into July and August, right? The sun is lower in the sky. Okay, so by the time December comes, the sun is all the way down here. So then it goes like this, right? So then when December hits, the sun is very low. And so it goes like this, right? So then you have A, and then this is the E. And then, so the flux is maximum in December. The flux lines going or not going through you, essentially, you see. So the flux is its maximum value in December 21. That's the beginning of winter, you see. So that causes the maximum flux lines trying to go through us, but they can't, in which case that we cast the longest shadow, you see. So this is your shadow. So if you're standing like that, this is your shadow in December. And if you're standing like that, your shadow in June is like that, much smaller. You see that? So your shadow is a measure of the what? The flux that's going through you, or the flux that can't go through you. You see? If you happen to be a transparent object, the opposite would happen. That those flux lines would actually go through you and you wouldn't cast a shadow. Do you see? People would just be able to see through you. Imagine if we were like that, transparent. So in December, people would be able to see through us the best. You know, we would be the most transparent. Does that help explain it, or does it confuse the issue more? No, I think it's pretty good. I think it's pretty good. So you cast the longest shadow, and that's the greatest flux. The least shadow, least flux. And if you happen to be living in more southern cities, you can actually get a flux that's zero if the sun is ever directly over you. Nice, nice, nice. Any questions on that stuff? No? Okay, that's cool. Okay. Okay, so what does where does Gauss's law come in? Gauss's law has to do with the flux through a closed surface, so not open surfaces. So the Gauss's law is saying that the flux through a closed three-dimensional surface is equal to the charge enclosed in that surface divided by E0, the electrical permittivity, which 8.854, I think, we saw that earlier, times 10 to the minus 12. And remember that the electrical permittivity is related to the Coulomb's constant. 1 over 4 pi E0 is 9 times 10 to the 9th. So it's equal to the Coulomb's constant. So E0 is just this portion, and it's a measure of how well vacuum can allow the permeation of electric fields. So measures how well electric field permeates through vacuum. Okay, so let's see, E dot dA is Q enclosed. So how do we apply that? So something like this: if you have a closed surface, you see, now the dA vector is more defined in terms of direction, right? So if you have a closed surface, on the left side, the dA comes always out of that three-dimensional surface. So on the left side, the dA vector is going to be like this. On the top, it's going to be like that, you see. So the two-dimensional surface, just like this, you don't know if the dA is this way or this way. Either one can work, you see. But if it's three, the dA always comes out of the surface. So on the side facing us, the dA is like this. On the back side, the dA is like that. On the right side, the dA is like that. And then on the bottom, the dA is like that. So then if you're given a certain electric field that's going through that surface, let's say something weird looking, like that. So imagine this is electric field. So then what it's telling you is if you integrate the electrical field along all that surface, along all that surface, along the bottom, along the left, and you take into account the direction of the dA and the direction between the E and the dA, you do all that integral, and if you get a zero answer, that means the net charge enclosed inside of that box must be zero. There's no net charge enclosed in that box. You see? So if the total flux across all surfaces was zero, then Q enclosed, the total is zero. In other words, it's not telling you that there is no charge inside. There could still be charge, but the net charge inside is zero, the total charge. So you could have a box like this with inside maybe negative Q and then another Q and then maybe 2Q, right? So then that's let's see, and then there has to be here negative 2Q, something like that, you see. So there could still be charges in there, but the net charge has to be zero. You see, 2 will cancel the negative. This negative will cancel that Q, you see. So it's not telling you there's no charges at all, but it's just telling you that the net charge of all combined charges are zero inside that box if the total flux through all the surfaces is zero, you see. But if the total flux is not zero, then that means there is more. Let's say if the total flux is positive, right? So if the total flux through all surfaces is positive, then what's the net charge inside? Positive or negative?
Negative?
No, if the total flux is positive,
positive.
Yeah, the total enclosed charge must be positive. In other words, if you have a box where there's more flux lines going out, let's say it's like this. You see, this one is going in. Let's see here. This one's going in, then coming back out. This one is originating in the box and it's just going out. This one's originating in the box, it's going out, originating in the box, going out. Let's say there's another one originating outside, going in, and then ending there, you see. So how many do we count that are going in? So this is going in, that produces a negative flux. This one's going out, that produces a positive flux. This one's going out, positive. This one's going out, positive. This one's going in and coming out. So we have to do the integral, see which one's bigger. So negative, positive, they might happen to cancel each other perfectly, right? So in other words, here I've got 1, 2, 3, 4 positive and 2 negatives. So it's likely that the net flux is going to be positive, you see. So if that happens, then that means the total enclosed charge must be greater than zero. So that means inside there must be more positives than negatives. So you maybe inside you have, maybe the inside looks like this. You have negative Q, positive 3Q, negative 2Q, and then positive 4Q. Something like that, you know. A weird distribution of charges. So if you, as long as you have more positive, in other words, as long as you have a bigger positive charge than negative charge, you know, you might have another negative that's negative Q. So you see, you have more charges here that are negative, but look at their magnitude. Negative Q, negative Q, negative 2Q. So together you have negative 4Q. Here you have positive 7q. So as long as the total magnitude of the positives is larger than the magnitude of the negatives, then you will have more flux lines coming out of that surface than in, you see. And then vice versa. The opposite is true if you have total flux is less than 0, then the net enclosed charge will be negative. So it's basically the Gauss's law is connecting the total flux through a surface in and out, right, to the net charge enclosed in the surface, you see. And if you have no net charge enclosed in the surface, then the total flux must be 0. So imagine you had something like this, a box, and you had no charges at all inside, and you had another charge outside here. What would be the total flux through that surface? Well, according to Gauss's law, if there's no charge here, the total flux through that surface would be 0, right? So if you draw the electrical field lines of a point charge, what does that look like? Goes through here, the left side comes out, goes through, comes out, goes through, comes out, like that, you see. So in other words, the flux coming through the left side must equal to all the flux coming out of the right side. In other words, it's not a very obvious thing to say, oh yeah, this law makes sense. Why is Gauss credited with even inventing this law? Because yeah, it makes sense that total flux should depend on the charge enclosed. But if you really think deeply, it's not that obvious that the flux going through the left, right, should be canceled with all the flux going through the right. Why? Because the electrical field here is weaker than the electrical field going in. You see, here I'm actually closer to the charge, so it's stronger electric field. Here the electrical field is weaker. So why should that be able to cancel that? At first, it's not very obvious, you see. Again, this one is also weaker than there. This one is also weaker than there. You see. But that's what Gauss is saying. As long as no net charge inside, the flux lines going in must be canceled with the flux lines coming out. Well, that's what I'm going to prove to you now by actually doing an example.